Cool. Thank you very much, Eli. My name is Kai. I'll now be giving a talk exploring zero-knowledge application alternatives and challenges. And this is more so going to be focused on product after going a little bit high level, and then talk about what the work that companies do produces in this space today. So high level, what is zero knowledge? What other solutions exist? Where does ZK get used? Where might it be used? And then what keeps it from broader use? First, similar to what Eli was describing, zero knowledge is frequently two results. It is verifiable computation, and then it's privacy. So the verifiable computation comes from the snark side of things, which is some process is run with inputs and outputs that generates a proof that anyone can verify this proof and be able to trust in it. So you have a dynamic of a prover and a verifier. And there's some computation that you want to run, which is just any process that happens, and you want to generate this thing such that someone trusts that it was run honestly and trusts in the result. I'm going to break it down a little bit more because it feels like this is important to move forward in understanding of ZK. An argument of knowledge is you have convinced someone that you possess some knowledge, and typically this is for a computationally bound verifier. Succinct means if you have a computation that's O of n, the verification must be sublinear in that. So that's either constant or log or polylog or something like that. If it were linear, it would, for example, be the same amount of work for you to just run the computation again. So there's sort of no gain there. And then non-interactive means that it doesn't contain an interactive protocol. So as Eli was mentioning before, there could be, for example, in a Sudoku, I could have a solution to it, and you could come up with random challenges within the board, which I say, oh yeah, I had 3 there, or I had 4 there. And through this process, through enough rounds, you come to trust that I, in fact, did have a solution, even without me revealing the full board. However, non-interactive means that we don't have to have that latency involved in back and forth, and we don't have to be live at the same time. And so any time that we can, through Fiat Shamir, get rid of that, we want to. And then the zero knowledge part is about privacy. It's that some inputs to the computation were private, and me having the proof, there's nothing extra that I've learned as opposed to not having the proof. How many people here roughly know zero knowledge, are familiar with it, have spent hundreds of hours in it? Hundreds of hours, okay, hundreds of hours. Okay. Well, I think this is more geared towards zero knowledge people who see zero knowledge as the hammer and everything is a nail. When some things are in fact screws, there are other solutions out there, and sometimes those are better to use. There's trusted third parties. A lot of the internet today relies on trusted third parties. This could be Google, this could be Facebook, that you have some interaction with them and you trust the incentives enough that you can trust them, right? I can give a post to Facebook and trust that they're not going to do something bad because it's bad publicity or it's too much work, any of these things. Trusted third parties, escrow accounts, these all fall under that. These are not a cryptographic primitive, but they're a great solution to many problems. So if you're not doing this, first, please understand why. But the reality is that Facebook does act in ways that we don't like, or these companies do act in ways that we don't like, and so we want censorship resistance, we want privacy. So another example is Signal. At some point in my communication with someone, I can trust that it's them that I'm talking to, and that everything that I'm saying is only readable by them, and that only I can read things they've sent. It might be the case that there's some side channel, some metadata that is revealed that I am in fact talking to this person, or the timing of when I'm talking to them. But symmetric encryption is a very strong tool that's well established. In arriving at that, we probably use asymmetric encryption, which is that I have some public-private key, I sign with my private key and your public key, and Through this, we first establish a session key, and then we are working with that. We do this just because it's much cheaper to use symmetric encryption. There are one-way functions. Hashing is one example. Merkle trees, which Eli described, is one data structure that uses that. Merkle trees show up in zero-knowledge a bunch. Commitment schemes show up in zero-knowledge a bunch. So a commitment scheme, very quickly, I have a value. I want to commit to it. And the properties that this protocol must fulfill is that it's hiding, that someone with my commitment can't learn the value that I've put in until I open it, and that it's binding. I can't commit to something and later switch to something else. It is, at the very least, unfeasible for me to do so. There are also mixed networks that sometimes people talk about, ZK solving, which is just a way for you to arrive at K anonymity, which is that someone seeing a chunk of data or a correspondence can't tell whether it came from me or any of the other K members in a group. And then there's more bleeding edge things like FHE, differential privacy, secure multi-party computation, etc. So quickly, FHE is fully homomorphic encryption. I have some data I encrypt. I put an untrusted platform like the cloud. Some function is run on it, and then it's returned to me. I decrypt it. I, at no point, had it in the clear, so I could be untrusting of this party. But the benefit of the work done is there for me. Differential privacy is that I have a data set that I somehow want to make use of. So medical records are one example. There are individual private accounts within that. And I want to somehow perturb this such that it loses some of its functionality, but not too much, while still ensuring the privacy of every member within it. So this budget of privacy in this process is differential privacy. And then multi-party computation is the ability for multiple people to be doing some computation together. And ZK is one tool that might support secure multi-party computation. So knowing the shape of your problem and then using the right tool feels very important. But I certainly want to argue that ZK is one tool in the toolbox that is worth a lot. I'll quickly describe two classifications of problems where you might want to use ZK. So the first is that, well, first of all, you have to have some untrust. Like if I could just run a computation and give you my solution and you trusted it, well, I should do that and I shouldn't do verifiable compute. I'm going to quote a paper which I will then properly cite at the end. One of the primary uses of ZKPs is the outsourcing of computation from a constrained environment to a computationally powerful, untrusted server. So asymmetric means that I have a constrained or expensive computation environment, and I have an unconstrained or relatively cheap environment. You can think of your computer to your phone as this, or your phone to your credit card as this. You can also see that the blockchain is relatively constrained and expensive, and off-chain is relatively cheap. So you might want to do your work off-chain and put the proof on-chain. But this doesn't just exist in blockchain world. For example, in a distributed energy network or power grid or something, you have microcontrollers that want to do some work but have very constrained hardware. And then there's the case of redundant work. So verification by numerous parties offsets the prover's computational load. This is, for example, if there are n different people that want to do the same thing. One of those people can do the work of generating the proof, which is more expensive than doing the computation, but then the other people involved just have to verify it. So instead of having n times the cost of running the computation, you have n times the cost of verifying the computation, which, as we've established, is sublinear. This is from Do You Need a Zero Knowledge Proof? By Jens Ernstenberg, Stefanos Chelaos, et al. Please look up this paper, it has great graphs. And I think that it can be very appealing to get involved in the math and the really nerd sniped down ZK. But figuring out how to actually use this with the right discretion is invaluable. So the main use case that I'll talk about is blockchain scalability. One example of this is rollups. how many people understand blockchain pretty damn well in this crowd? Put your hand up if you're good with blockchain. That is a very low number of people. Okay, so blockchain, decentralized network where a ledger establishes what is true, transactions represent changes to state. This is roughly the case generic across blockchains, right? And you can expect in this environment that if it's all throughout the world and I put a transaction out there that I want to affect the state, and then everyone has to agree on it, it has to be finalized, and this has to happen every time something happens, this scales terribly. So instead we want to batch a bunch of transactions, frequently on a layer 2, and we call this a rollup, that when that reaches finality, it then affects the underlying L1, which then expresses, oh, I understand that I'm in this new state. And you've gotten tremendous scaling gains. So this comes in two main forms. The first is optimistic, which, true to its name, is just someone makes a roll-up and puts it out there, and people trust it by default. And there's a timing window in which any of a number of specific parties can express that it was fraudulent in some way. And actually, one of the first places that ZK shows up is in Owen Labs has put forward to Optimism a ZK fraud proof. So instead of each of these parties having to establish, oh yes, this was fraudulent for these reasons, you can just verify that proof, which is on sort of the state of things. But then the main thing that we talk about here is ZK rollups, which you can instead trust a computation that a batch of transactions is in fact valid and is moving you to a new valid state, and then believe that just by verifying this ZK rollup. And you don't, so invalid might mean that someone now has negative money, they've spent money twice, that sort of thing, right? You're guaranteed that that is not the case. A number of other places where blockchain is affected by this technology involve, so interop, which is bridging. Essentially, if you have two different chains, two different ledgers establishing things that are true, you probably want to go between them at some point or move money around, that sort of thing. That is bridging, and that also uses ZK in some cases. And, I feel like there was one more, but I forget it now. There's data availability, but that isn't what I was thinking about. Okay, so the other use case is the ZK part of things. There's the privacy. There are privacy-preserving chains and rollups for making apps, and this essentially means that the tools for having private inputs or doing private computation is readily available to you if you're working in one of these environments. So Aztec is one good example. There are several others. There's also Zcash or other chains or environments in which payment can be private. And there are private auction situations like Anoma's intent-centric auctions, which, so it is eventually posted on the ledger that some auction happened. Do people roughly know what I mean by auction? People don't know what I mean by auction. Okay, something is put out to be bid on. Does this make sense? And the source of the bid, the source of the asset, the amount that different people bid, it can be kept private to everyone involved until like an auction clears, and maybe even the price of how much it went for is kept private afterwards. And you can imagine that you don't have to think of Web3 in this context. You can imagine like eBay wants this, or bidding on ad space wants this. Like the majority of Web2 money goes into ad auctions, and like this sort of thing is very interesting. You can imagine why. This also enables proof of identity when you have like provable privacy. So WorldCoin is one that does this, takes biometric information, posts that to Ethereum blockchain, has gotten millions of users in that way, and it exists in a way that you can interact with and prove who you are without revealing critical private information about you, which you can imagine is very important to you being biometric information. There's also modern ZK companies, more product focused, who just, for example, take an Ethereum address and prove that you have a given Twitter handle or other social media handle in Web 2 as a way of connecting those pieces. Where might it be used? So some of this has been tried, but I'd say that all of this hasn't really landed, but there's a lot of interest in it. I'm most interested in ZK-ML. Who knows what auditing is in the software world? Is anyone? Okay, that's a good show of hands, yep. So your software or your model being like a machine learning model in this case, might want to be audited for a variety of reasons. Either it's critical to you and you want the right specialists looking at it, etc. However, many companies in AI, a lot of sort of the value that they hold is in these models. And if you just put it out there or risk that in a variety of ways, that's a big deal for you. So being able to audit it, which is essentially engage with the shape of it, making sure that it meets certain criteria without putting yourself at that risk, is very interesting as a use case. And then there's proving inference time consistency. So ML frequently works by training time and then inference time. Inference time is more things like, oh, this image is a rabbit, in fact, or this is a cat, right? But you, for a variety of reasons, might want to see that a model that's being used on you, with you, is not changing, so it's not biased in response to anything. Or it's something you're somehow engaging with financially, and you want to just see the consistency there. And that is by verifiable computation on your engagement with a neural net. There's also supply chain. So supply chain is a big deal. It's getting raw resources to some final product in a consumer's home. And in this modern age, much of the process involves some digital engagement, right? There's measures of time or temperature, etc. And there's probably some regulation in place as things move between countries, or there are food regulations, etc. And okay, I really want to get this point across. People think of computation and crypto and all these things as complicating things, but the reality is that we have all of this legal infrastructure or other processes that take up tens of thousands of dollars or hundreds of thousands of dollars to engage with and get through. And when you find a solution that uses this, you can get that value because you are providing that value. So through this supply chain, many of these parties want to hold information private because, for normal capitalist market reasons. However, they're willing to expose other information in an effort for some buyer to be assured that there's some quality guarantee about the metal they're buying or the meat they're buying, etc. Right? So this becomes very interesting, both the privacy and the verifiable compute. And then there's voting. People talk about voting often. I think legislation and getting it right across different countries is super hard, and I just don't always like thinking about it. And especially with things that aren't a standard, there are cryptographic standards that get approved by different countries. I think the US is definitely the one that matters the most. But that comes up in supply chain and then also in voting. So it's something big to consider before you start engaging with this problem. And then voting isn't just a problem of technology. It's about implementing it right in a technical space and a people space, and then getting people on board. And there's just so many ways to get it wrong, and it takes so long to get approval for this sort of thing. So while I am very excited about voting, and I think that voting could be done much better, and people have tried this, it is rough, and I don't know, be wary of that. What keeps it from broader use, and what do companies put energy into? So very quickly, it's developers engaging with this stuff in the first place. It's ways in which it's different from most existing tech stuff. and kind of like not interoperable with tech stuff. And then it's scaling decisions around prover, verifier trade-offs. So first, representation differences. In zero knowledge, it's frequently, well, you have circuits. People understand algebraic and Boolean circuits. And then you can have plunker circuits, which just like give you extra behavior, but like essentially do the same thing, because circuits are NP complete. You don't exactly need to know that, but that's going to come up in the scaling example in a second. There's a lot of finite field math on polynomials, and finite fields have, like many of the ones that we pick are large enough size that they don't fit in normal hardware, which becomes a large issue. So how you're representing the numbers that you're engaging with is a large issue, and some paper might come out and it does all this work, like circle stars, and the only result for you is that you get to pick a better finite field size, in this case one that fits in U32, or you have like Phineas with binary towers such that you can like do operations faster, and like the full 32 is covered. So things come out like that in order to make it more interoperable with existing hardware. There's also ecosystem. So if you wanted to run an app on your phone that does something like this, and it was a computation of any reasonable size, any interesting size, that would be quite hard for you. But if you could send this to a service, say, I want to do this computation, give me back the proof, and that service could somehow handle that for you, that would be great and enable a bunch of use cases. And there's also hardware. So if we are using large finite field sizes and we need larger hardware, FPGAs, or hopefully not ASICs, companies put energy towards doing that part of things as well. And I mention these in tandem because with proof markets, you then are like distributing this to a bunch of provers who get to specialize and who get to choose their hardware, and for them it makes sense to perhaps buy custom hardware to do this sort of thing well, versus for a consumer on their phone it doesn't. There's difficult development experiences, so even iterating on apps that use zero knowledge is quite hard. If you are a software company and you want to use this sort of thing, then you like need a protocol engineer and need to invest all this time and energy to even try to make use of it. And virtual machines over the last year or two were a very popular, understandable solution to that, such that I, a developer, can write in my native language, like Rust or TypeScript, and all that I need to know is that that computation is being verified, or that some inputs to it are private. It makes the lift much lower, and then you can iterate much better. How many people know what a virtual machine is? Most people? Okay, great. And then there are trade-offs of proof or verifier. We mentioned that maybe your verification can be O1, how much you care about the prover's time or memory, because these large circuits take up lots of memory, versus the verifier's time. And there's a number of other considerations like the trusted setup or the trust assumptions that you make when you start doing this, interactive protocols versus not, and then quantum secure, which, as has been mentioned, it matters less in ZK. So forward privacy matters a bunch of like encryption standards, right? Quantum computers aren't really viable today or exist today, but if I encrypt something and expect it to stay encrypted for 20 years, I need something quantum secure maybe, versus a zero knowledge proof, unless you are somehow like breaking the proving part, it just like doesn't matter in the same way. I could get more into that if people are particularly interested. How much time do I have left?
6 minutes.
6 minutes. Okay, great. I'm Geffen. With the help of other people, we've put on ZK Dive to try to get the ZK community in New York City a little bit stronger, because I know it's there, and we have to go to Europe every time we want to go to a conference. So ZK Hack, if you're getting into ZK, is one of the best places to get started. It's a Discord, they have summits, they have hackathons, they have hard cryptography, medium cryptography, medium math. It's a great time. So feel free to scan both of these, and I would love to have any questions if people have questions, maybe more so geared towards like product. Yes?
Out of curiosity, what are you working on that uses ZK?
So I'm not working on anything currently. I worked at Ironhill previously, which did developer tooling, because I thought that was a very important area. Having gone to ZK Hacks, it's just like fairly inaccessible to get started with this stuff. And like the niceties that you'd come to expect, like a package manager, like version control, these sorts of things, hosting, just like wasn't there. At the moment, I'm doing this, and then next, I don't know, maybe I'll look into ZK and I'll lose a couple of papers I want to read. But yeah. Any other questions?
What are
Any?
Was this time for like, oh, would this product be makeable?
Yeah, sure.
Okay. So like one thing I thought about is like having basically like the ability to trade secret information. So like on a blockchain, you would say like, okay, I'm not gonna tell you what the secret is, but like I proved that I know something, and then if someone buys it, like we have to make a proof that now they know it too, or they get their money back, or whatever.
Is it okay for them to know it?
Yeah, they bought the secret. Yeah.
Okay.
But no one else can know it, just the person who bought it.
So it couldn't just be that I encrypt something and then I sell it to you because you also want it to unlock as soon as it's bought by that person. Is this correct?
Yeah.
I do think that you could use ZK for that, yes.
I have an answer. There's like a really beautiful way to do this. It's like one of the first examples that got me excited about ZK. There was a thing published for Bitcoin in like 2015 called Zero Knowledge Contingent Payments. So the idea is they did a pay to Sudoku thing. So the idea is I have a really hard Sudoku problem. You want to buy the solution from me, and I want to not give you the solution until you've paid me, and you want to not pay me until you have the solution. So what you do is I make a zero knowledge proof that I have encrypted the solution with a particular symmetric key, and I don't give you the symmetric key. I also prove that the hash of the symmetric key is a particular hash, and then I basically, on the Bitcoin blockchain, can do a pay to hash address for that, meaning that if you pay to the hash, the only way for me to draw the funds from this contract are to reveal the encryption key, which you have I reveal the encryption key on the blockchain. That's the only way for me to draw the funds, and you have the encrypted solution and the knowledge that by me withdrawing that you are now able to decrypt it.
There you go. This is why we have this room full of people. How are we on time? Do we have one more question? Good. Any more questions?
Yeah. What are some like hardware requirements for doing ZKML inference and yeah, just curious to know.
Well, he's much better at hardware than I am. There are several people who are better at hardware than I am. I will say that so AI became popular and became funded a bunch, and then like quantization became a thing that was achieved kind of from that side, where instead of floating points, you have representation in natural numbers. And that kind of bridges the gap between working in finite fields and working with models. Hardware-wise, what it takes, like ZKML isn't quite there. There's a couple of companies working on it, and people are excited about it. I'm not sure if it has more hardware considerations than the average problem, but there are people with better information about that side of things than me. Yeah, thank you.
I mean, there's no time to, well,
Just 50 seconds.
okay. Well, basically, I feel like the thing that I want to know now is like someone you described the Sudoku thing,
Yeah.
and it's like, okay, I don't have any intuition about how that was made. Like, did they make, like, what were the inputs? Even if I have like this VM thing, like, did they just make a program that verifies solutions and then proves that the program really verified it? Or did they have to like show, like, did the Sudoku solver program have to be like open source and then they just showed that they ran that program?
Yeah, so the computation.
Did you want to say that? Okay. 5 seconds.
You do have images of the computations. Like, you agree on the computation running with the verifier.
So, but you can't just have a computation that's like, this thing verifies Sudoku solutions and then the Sudoku solution is secret, and that works. It has to be like the actual solver.
What's the verifier?
Just the verifier. Okay. Alright.
Yeah, okay. Great, so the next speaker, I guess I'm transitioning out of my talk. The next speaker is Maciej, who's just gotten off a plane from Chicago, and I should look at my phone to see if he's here or not, but he will be here very shortly. And then after that, we'll have a panel with a couple of us getting up more geared towards answering questions that you might have at this point.